So this section is called nonlinear functions. And we know a lot already about linear functions, right? Linear functions are just lines. And so in some sense, there's not really anything else that we can even learn about lines. Oh, that's not, there's always things you can learn. But the reality is you know most everything about lines, how to find slopes and intercepts and equations, and how to graph those lines. So we have a complete understanding of lines, and that is one type of function. But there's many, many more types of functions out there, and all of those would be nonlinear functions. And there's different kind of categories of these functions. And basically, as you move through this course and college algebra, and if you continue on into pre-calculus, you study sort of different groups or classes of functions, and you learn things about them. Some types of functions you'll have a full understanding of, like you do lines, but a lot of types of functions will just get kind of an idea how they work. Some general properties of them, we won't know specifically everything about them. So nonlinear functions are not going to be lines, and for us there's some very basic versions that we want to know, and some of these you may already know. So one nonlinear function is f of x equals x squared, and you can always figure out these functions by plotting some points, right? But you don't have to start over with plotting points every time you have a new function. So this f of x equals x squared is like one we'll see all the time, and you just want to know it looks like this. There are some points here that are common, like this +1, -1, right? When you put in 1, you get 1. When you put in -1, you get 1. And there's this sort of central point here, which is called the vertex. We will learn more about this x squared or quadratic parabola function later in the course, but for right now, just think of that as a sort of a basic template, a building block. We also want to work with the square root function. The square root function isn't defined for negative values, so that's not in its domain, right? We can't put in a negative and take a square root of that. We would get what's called an imaginary number. Excuse me, but that's not on the real axis here, so we don't have those values as valid inputs. So we only get positive, non-negative values. 0 is okay, and it goes up like this, right? And again, you have this 0.11, right? When you put in 1, the x value of 1, right, square root of 1 is 1. So that's our square root function. We also have the absolute value function. Right? The absolute value function always has an output or a y value that's positive, right? So notice all the y values are up above because they're positive. And it looks like this kind of V-shaped version. And these are really our main 3 for right now, but you will also see x cubed, which looks like that. And sometimes, in terms of these basic functions, sometimes the books will include f of x equals x, which is just this linear function, this straight line. But I kind of like to separate that. We already know what to do with lines, so we don't really need to study them again. We don't really know what to do with all of these different types of functions. So these we need to look at a little more carefully. And the idea is, from these basic functions, we can create infinitely new functions by making some sort of changes. So one type of change is called a shift, and we can take either a vertical or a horizontal shift. In order to shift a function vertically, what we're going to do is we're going to add or subtract k to the function value. And what that's going to do is it's going to move it either up or down from its original place. So the example of that is if you see a function that looks like g of x equals x squared plus 2, the whole point of this is that we recognize this new function g of x as being just a transformation or some change of this original function x squared. I don't want to start all over and think g of x is some totally new function that I got to figure out what it looks like. I want to build it off of what I already know about functions. That's the key idea, and that's really it's really an important and powerful idea. And that's really, to be honest, what we want to do in math all the time. I don't want to start over. I spent a lot of time learning a lot of stuff, right? I want to use all that stuff I learned rather than having to start over when I see a new problem or a new situation, right? So as mathematicians, we work really hard to connect new ideas to old stuff we already know, right? And that's what we're doing here. It's not a new function. This is just an old function that's been shifted. And so we can come up with a graph here by just taking this old function, right? That's like the original old function, and the plus 2 shifts everything up 2 units. So it looks like that. So what we're really looking for here is this graph, right? If I give you this function, you can come up and visualize and sketch this graph. It may not be perfect, but it's showing us a representation there. The same thing works with negative values, and it works with any function, not just these 4 functions. You can really do it for any of these or any other functions that we're going to run across. You can do the same shifting. Negatives would, of course, bring it down. We also have horizontal shifts here. So horizontal shift would look something like, let's say g of x equals, oh, I should write it out like this, f of x plus or minus k. So the difference here is that to shift it horizontally, we want to change the x values. Here we're really changing the outputs or the y values. That's why it's shifting it up and down. Here we're changing the x values, which is moving it left or right. So an example of that is if I have x plus 2 squared like this. Because here I've changed the x values first. I've changed the location, the left and right values, so that's a horizontal shift. Now the one sort of tricky thing about horizontal shifts is they work a little bit opposite as to what you might guess. Normally we would think plus 2 would move us to the right, but actually it moves the graph 2 units to the left. It does that because it really, like, this is the x value of minus 2. And when I put minus 2 in here, it functions just like 0 would in my original graph there. So, you know, it's very clearly there's a reason of why that works. But I think a lot of students just remember it does kind of the opposite of what you might expect. And that's really a perfectly fine way to approach that problem, right? It does the shifting, but it does it the opposite of what you might imagine, right? Left and right. Questions about those so far? I could have done them with any. They didn't have to be the squared functions. They could have been the cube root or the cubed or any of those functions. Any questions? Okay. We can also have what's called a flip. So a flip is where the function either flips kind of up and down or left and right across the axes. So I call a vertical flip the up and down, and that happens by putting a negative in front of the function. So it takes all the positive values and makes them negative, and it takes all the negative values and makes them positive, and that's why the function flips. So negative, the absolute value of x, that takes all those positive x values that I started with and flips it over so that it looks like that. So you might not be surprised to realize that a horizontal flip comes from making the x negative, right? Flipping that x value from positive values to negative values, which gives us a horizontal flip. Some functions are symmetric, so it doesn't matter. Like if I flip x squared horizontally, it looks the same as what I started with, because of course f of minus x is equal to minus x squared, which is just x squared. So for some of these functions, you can't tell the vertical or the horizontal flip, but some of them you can. If g of x is equal to the square root of negative x, that takes our original square root function and flips it horizontally. Okay. There are some other types of these transformations, but these are the ones we're really focused on in our algebra course. So you can put some of these together too. So for example, if I say graph h of x equals negative absolute value of x plus 2 minus 3. Well, what we want to see there is that that's an absolute value function that's been moved left 2, vertical flip, and down 3. So all 3 of those transformations. You can do it all at once, but sometimes people find it helpful to kind of sketch that in little pieces, right? Like that's my original. So left 2 would be here. The vertical flip would be here. And then down 3. So it'll end up looking like that. Okay. So that would be our graph that we're looking for. And it's super nice because then we're not starting over, right? It's like once you learn these skills, you can take, you know, what looks like kind of a complicated function, maybe something it feels like we haven't seen before, and recognize it really being built from something we already know. Any questions from any of those ideas of nonlinear functions and transformations? I will tell you that it is important to me that you are able to sort of list these. Sometimes people's graphs don't really match what I think they might have been trying to do, right? Like an art problem somehow. If you can tell me what the function has done and you show me that you know your sort of basic version of the graph, you know that an absolute value function looks like this V, then you're going to be in good shape points wise. But if your graph is kind of off of what it should be and you don't list what those changes are, then I don't know if you know what you're doing or if you don't know what you're doing, right? So kind of make that a habit of just just making a little note of what each of those transformations is doing to your original. As we move through the course, we'll add a couple other kind of basic functions to our list, but this transformation strategy works the same no matter what starting function you have. As long as it's a function, you can do these same transformations. Okay. No questions? Okay. So I'll just talk kind of briefly here about systems. That's our next section. So some of you may not have started on that, and that's fine, but you'll start shortly on that. Section 3 is kind of broken into two big chunks. There's chapter 4, which is about systems, and then there's chapter 5, which is about polynomials. And you should probably have had some experience with both of those topics in some form. So parts of it will be review, but typically parts of it will be new as well. So, you just want to, go through the parts you know and feel comfortable with, but always be on the lookout for any kind of errors in thinking that you might have. So a system looks something like this. 2x plus y equals 6 and x minus 4y let me think of some good numbers. Let's try that. Equals minus 6. Okay. So a system is two equations that are related. So the x and y here mean the same thing for both of these equations. And what we want is we want a solution, an x and a y, that makes both of the equations true. It's pretty easy to find solutions to one of the equations, but they're not always going to match the other equation, and that's really what we want. And we're focused here on linear systems, so our equations have no x squares or x cubes. If you take college algebra, you'll see some nonlinear systems. But for right now, we can focus on linear systems, and these are even extra nice because you know that these are lines. Right, 2x plus y is some line, right? It actually looks, I think it looks something like this. And this x minus 4y equals minus 6, that's some other line. That line might look like, I don't know exactly what it looks like. It's something like this, right? Those lines are solutions to those equations. And I think you can guess where the solution is, right? The solution we're looking for is this one point right here, because this point is on this line and it's also on this line, right? So that point is really the solution that we're looking for. Now, I haven't graphed the lines accurately, so I don't know where this point actually is. And even if you did graph the lines accurately, you may or may not be able to actually figure out what that point is. So the graphing method is good for the idea, but it's not so good for actually finding it, right? So for actually finding it, we want to use either what's called substitution or elimination. So those are the two primary tools that we are going to use to solve these systems. And they both can solve any of these systems. So you could use always substitution or use always elimination, but there are situations where one is easier than the other. So we do want you to know both of them just in case. So I'm going to solve this system using both of these tools, and then we'll probably see where that gets us. But The idea of substitution is that I'm going to solve one of these equations for one of the variables. And it doesn't actually matter which equation I solve or which variable, so I'd like to keep it easy. This top one wouldn't be very hard to solve for y, but the bottom one to me is almost easier to solve for x, because then it makes this a plus 4y minus 6. Right, just by adding that 4y over. They're just equations, so you can add or subtract both sides or multiply both sides by whatever you want, and you keep the same solutions. So this is the same or equivalent system. And then the substitution is I'm going to replace the x there with this value. And that's going to give me an equation that I can solve. So notice now I have an equation that just has a single y value. Y plus y is 9y. Add the 12 over, I get 18. And I get a value for y equals 2. Now this is great, but I'm not actually done. It tells me the y value of my solution is 2, but I also need the x value. I can plug this y into either one of these equations. The bottom one is perfect. That's one of the advantages of substitution. Eight minus 6, x equals 2. So my solution here is 2, 2. The x is 2 and the y is 2. Okay? So that's our goal there with that substitution method. Elimination is kind of the same idea. I want to get rid of one of the variables, but we're going about it in a different way. The way we do elimination, and it's also called the addition method, is I'm going to add these two equations together and hope, well, not just hope, I'm going to make sure that one of the variables cancel. Right now, if I added them together, 2x and x would be 3x, y minus 4y would be minus 3y, and I wouldn't be any better off than where I started. I just have x's and y's again. So what I'm going to do is I'm going to multiply this bottom equation by negative 2. Be very careful here that you don't make a little error, right? I've got to make sure I get all my signs and values right. Now I can add these two equations together, and notice those x's are going to cancel.
I have a question.
Yes.
Why did you minus it by negative 2?
Okay, so the reason I multiplied it by minus 2, I multiplied both sides. And first of all, I can do that because it's an equation, right? So I didn't change it because I did it to both sides. I needed that so that when I added these two equations together, the plus 2x and the minus 2x canceled.
Okay.
You could have also multiplied this top equation by 4. That, notice, would have given you a plus 4y and a minus 4y, which also would have canceled when you added them together. Okay?
Okay.
Either one of those is perfectly fine. I just want to find kind of an easy combination so that when I add them, they cancel. And notice when they cancel, now I have just a single variable, and kind of like before, it's pretty easy to solve for the y value, and then you can go and substitute back this into either of the equations to figure out what the x value is. And of course, we get the same solution because it was the same system. Right? So that's a point. That point there is on both of the lines, and that's the solution that we're looking for. It's pretty standard kind of questions for us. And getting those basics down is going to be, you know, really useful. This also leads very well into some application problems. There's a lot of times where you don't know two things in an application problem, and so a system can be a good way of solving an application problem too, because it includes, as long as you have two equations that you can generate, you're going to get your two solutions from that. Okay. I'm going to take just a quick second here, 2 minutes. I'll step away, and then I'll be back to see if you have any questions. Okay.
Okay.
Okay, I'm back. Do you guys, let's see another example or situation of systems here. Okay. So there's a couple kind of special cases that can happen with systems. Remember that there are two lines, and so sometimes, like the last one, they meet and those lines have a an intersection, but sometimes they don't. So we could have the two lines that look just like that, and those lines wouldn't have any solution because there's no point that's on both of those of those lines. So the question is, how does that work algebraically? Well, it turns out what you'd end up with is something like this. So these are the two lines, or two versions of lines. And what we'll see, and you may see this already, is that the x's and y's are actually almost the same, right? One was just multiplied by 2. So what happens is when you try and do either substitution or elimination here, this one is going to be best, I think, by elimination, because if I try substitution, I have to solve for x or y, and it's kind of a pain to solve for x or y. I can do it, but I'll end up with some fractions. I don't really like working with fractions. It's much nicer here to do the elimination. And here I would multiply this whole equation by -2. Maybe that's what I did last time. That's just coincidence. That gives me -4x minus 6y equals -12. And that's the bottom equation just recopied. So now notice when I add those together, both the x's and the y's cancel. And I get 0 equals -8. And this is clearly false, always. I can't do that. That's really what this is telling me here, is that these are always going to be false. No matter what solution I pick, I can't solve both of them. So this is what's called, well, the simplest thing is just to say no solutions. You can also say it's inconsistent. That's a more mathematically precise term, but they both work great. Okay. Now,
Sir, can I ask you a question?
Yes, please do.
What section is this?
Yes, this is from section 3, kind of homework 1 and homework 2. So you guys haven't necessarily started on this yet, right? This is
Okay.
what you'll be getting on next week. Yeah.
Okay. Thank you.
Yeah. So if you haven't seen it, don't panic. You're fine.
Okay.
So the sort of unusual thing here is that both the x and the y dropped out, but that can happen and not be a no solution situation. So it's possible that when we sort of did this work and the x and the y cancel, you might instead get an equation that looks like this. Maybe 2 equals 2 instead of 0 equals -8. And 2 equals 2 is always true. So that's a big difference. That turns out to generate infinite solutions. It's called dependent. And graphically, what that looks like is that the two lines are actually right on top of each other. So it's not true that anything works, because these points over here wouldn't make it true, but any point on any one of the lines will solve both of the lines, because they're really the same line. And so this one's a little tricky because we have to write our answers in kind of a special way. So here's an example of what that might look like. Let's say x plus y equals 3 and 2x plus 2y equals 6. So I think pretty clearly you can see that these two equations are really the same equation, right? This one is just multiplied by 2 to get the second one. So when we do all the work, we will get something that looks like this. So the solution, what we're going to do is we're going to write it like this. We're going to write, it's the set, this curly bracket means the set, it's the set of all ordered pairs such that, you don't need that underline there, such that, and then you're just going to write down one of these equations. It doesn't matter which one because they're both the same equation. X plus y equals 3. So this might sort of feel or seem a little kind of funny or unusual or something to you, but it is the way we need to write it, because we can't just say anything works, because that's not true. There's lots of points that don't work, but we can't just give you a single value either, because there's lots of points that work. So this is like the mathematical way of writing that down. Okay, so basically the only thing that's going to change for you with these different dependent problems is you're just going to put a different equation in there. Questions about that at all? Okay. So the majority of the problems, I mean, it wouldn't have to be, but the majority of the problems just have one solution. Right? There are two lines and they just happen to cross somewhere, and you want to figure out where they cross. And we do that algebraically with the elimination method or the substitution method. But there are a fair number that fall into these special categories. They can either be no solutions or they can be infinite solutions. You cannot just leave your answer like that. That doesn't really say anything. 0 equals -8, like, what does that mean? You need to state something along those lines. No solution or no answer, or it doesn't work. There's lots of ways of saying it, but you got to say something. Okay. Any other questions? Okay. If you did have something, you're welcome to stick around. Remember, no Zoom, no sort of scheduled Zoom time next week during President's Day, but I will be available for questions as normal, and then we'll meet again the following Monday. And then, right, make sure you're wrapping up your homework and your quiz and your take-home work. So all 3 of those are due tomorrow. So make sure you're close to getting those all done. And then as soon as you're done, you want to get started on the section 3 as soon as possible.
Okay.
Oh, section 3 is 2 chapters or 1 chapter?
It is 2, yeah, good question.